Okay, so we'll start the class now. In the previous class, we discussed about design of helical springs under fluctuating load. So in that discussion, we derived an equation to find out what is the factor of safety against the given loading conditions for a chosen spring. So we already discussed this one, this diagram, which is going to be the design criteria for the springs against the fluctuating loads. So I'm not going to discuss that again. Anyway, we already discussed it. So finally, what we need to concentrate on is this is the equation what we have to use when the spring is subjected to fluctuating load. And also we have seen that all the springs are subjected to pulsating loads only, not a completely reversible loads. That's why you have to choose this SSC dash differently from the conventional approach. So now we know for a given material you can find out what is the ultimate. This SSC dash is nothing but the ultimate shearing strength against the giving the fluctuating load, and tau A is the amplitude stress and tau M is the mean stress. So we need to calculate tau A based on the amplitude load, and that too you need to apply while calculating this tau A, you need to apply the correction factor as K, which is the product of Kc and Ks. For K is product of Kc and Ks means it will include both the effects of direct load, direct stress as well as effect due to curvature. Whereas while calculating this tau m, you need to use the mean load Pm and you need to apply the correction factor only Kc, that is low stress correction factor due to direct shear stress only. Then SSY, so that is yield strength in shear. This is a material property. You need to pick this value from the data book or given from the given material properties. You need to pick this SEC dash and SSY. Then apart from that, you have only factor of safety. So if you substitute all the data into this equation, you will get the factor of safety. So now from this equation, if you get your factor of safety is as per the requirement, then you can say that the design of the spring is okay. Otherwise, you need to modify the dimensions of the spring such that you will get the required factor of safety for the spring against the fluctuating load. Right. So now what we'll do is we'll take up one or two problems on this and we'll close this topic also. Okay, so in that, this is the first problem. Just you note it down this problem. So I'll give 2 minutes time to note it down. Then we'll discuss the solution also. So now note it down this problem. Then we'll discuss the solution. A helical compression spring of a cam mechanism is subjected to an initial preload of 50 newtons. The maximum operating force during the load cycle is 150 newtons. The wire diameter is 3 mm, while the mean coil diameter is 18 mm. The spring is made of oil hardened and tempered ball spring wire of grade VW with SUD 1430 Newton per mm square. Determine the factor of safety used in the design on the basis of fluctuating stresses. Okay, so now just note down. It won't take much time. So even 1 minute is more than for this, more than enough. Just note it down, then we'll discuss the solution. Okay, so I think you might have noted down. Okay, so now we'll see the solution for this problem. So now, if you look at the problem data, here he has given all the parameters of the spring. He has given the Y diameter, which is 3 mm, and also he has given the mean coil diameter. So that means no need to design anything here because he already given the dimensions of the spring, so no need to design anything. So that's why in the problem itself he asked us calculate only the factor of safety against the fluctuating stresses. So that means you need to use this particular equation. So now in order to use this particular equation, you need to calculate what is tau m, what is tau a, and then what is SSY and what is SSE dash. So you require these four things only. So like I already tell, you need to calculate tau m based on the mean load. So for mean load is nothing but the maximum load plus minimum load divided by 2. So in the problem he has given the maximum load as 150 newtons and minimum load as 50 newtons. So you can calculate P, you have P max and P mean, you can calculate P max mean. PM is nothing but average of these two. So then, since he has given the D value, capital D and small d, you can calculate the spring index. Spring index is nothing but capital D by small d. So both the values are known to use, so you can calculate C. Once you know the C value, then you can find out what is Kc value, that is shear stress correction factor due to direct shear stress, which is nothing but 1 plus 0.5 by C. So we know the C value, then I can now calculate Kc value. So I have PM value. So using this PM and Kc value, we can calculate tau m. Tau m is nothing but Kc into 8 PM into D by 5D cube. So you can calculate, first one is tau m. Then you have to calculate the next parameter, which is tau a. For tau a required, you need to calculate K factor. K factor is nothing but, again it is a function of C. Once you know the C value, we can calculate K, which is nothing but 0.41 1 minus 4C by 1 4C minus 1 by 4C minus 4 plus 0.615 by C. So that means you can calculate K also. Then while calculating tau a, you need to use in the load, wherever P is there, you need to replace that load by PA. You have to use amplitude load, which is nothing but P max minus P minimum by 2, that is 150 minus 50 by 2, which is nothing but only 50 newtons. So now we get tau m and tau a. Then he has given the material for this one also. The spring is made of oil hardened and tempered wall spring. So therefore, for oil hardened and tempered wall spring, so you need to use your data book to identify what are the properties of SSE dash and what is SSEY. So that I already given those values to you. So now if I go back to the data again, here, okay, so then this is patented and cold drawn steel, these are the properties. Then for oil hardened and tempered steel wire with VW grade or SW grade, so these are the properties. So your SSE dash is 0.22 SUT, SSY is 0.45 SUT. So SUT is given in the problem. Ultimate. So SUT is given. So then you can use that SUT value to compute what is SSY and what is SSE dash. So that's it. So in those equations except Fs, we know everything. Then you can solve that equation by substituting all these parameters. You will get the factor of safety. So now I'll show you the calculation part also. So coming to the calculation part now, this is the given data. P max is given as 150 newtons, P minimum is given as 50 newtons, Y diameter is given as 3 mm, and mean coil diameter is D. Capital D is given as 18 mm. So SUD is given as 1430 Newton per mm square. So this is the entire thing. This is the data what he has given in the problem. So now first we need to find out what are the mean stresses and what are the amplitude stress. So for that, like already tell, for that first you require C value. C is d by d. So d, capital D is 18 and small d is 3. So we'll get capital C as 6. So that is spring index. Then you can calculate factor K, that is wall shear stress correction factor. This capital K is used to calculate the amplitude stresses. So which is nothing but 4C minus 1 divided by 4C minus 4 plus 0.615 by C. If you substitute C is equal to 6 into this equation, we'll get K as 1.2525. And similarly, we need to compute the stress correction factor, shear stress correction factor due to direct shear stress only. So Ks, which we need to use to in calculation of this mean stress. So which is nothing but 1 plus 0.5 by C. So again, if you substitute C is equal to 6 into this equation, we'll get Kc as 1.0833. Then your mean load, that is nothing but P max plus P minimum by 2, which is 150 plus 50 by 2, we'll get it as 100 newtons. And PA is nothing but P max minus P minimum by 2, which comes out as 15 newtons. So now I have everything. So to compute what is tau A and tau M. So first we'll calculate tau M. So tau M is nothing but Ks into 8 PM C divided by 5D square. Just now we computed what is Ks and what is the mean load. So we substitute the data here. 1.0833 into 8 into mean load is 100 newtons, C is 6 and the wire diameter is 3. So by substituting this data, I will get your mean stress as 183.91 Newton per mm square. Similarly, we will compute the amplitude stress also, that is tau A. Tau A formula is capital K into 8 into PA C divided by pi d square. So we already calculated this capital K, which is 1.2525 into 8 into PA, that is the amplitude load, which is nothing but 50 here into 6 divided by pi d square. So D is 3 mm. So that's what he has already given in the problem data. So by substituting that, you will get 106.32 Newton per mm square as our amplitude stress. So once you have mean stress and amplitude stress, then you need to calculate the factor of safety by choosing those two parameters, that is material properties. So for oil hardened tempered steel wire, your SSC dash is 0.22 times SUD. SUD is given as 1430 Newton per mm square. If I substitute that, I'll get SSC dash is 314.16 Newton per mm square. Then similarly, you required SSY, that is yield strength in shear. SSY is 0.4 times SUD. So then substitute that SUD value, we'll get it as 643.45. So now once you have tau M, tau A, SSC dash and SY, take these four values and substitute into that formula for the factor of safety. So this is the formula for the factor of safety. So in this, I'll substitute these four values. So I'll get, this is the equation by substituting all those parameters. Your tau A, we got it as tau A as 106.32. Then SSY, we got it as 643.45. Of course, I'll keep Fs as Fs itself. Tau M, mean stress is 183.91. I'll substitute for that. SSC dash divided by 2. SSC dash, we got it as 314.16 into 1 by 2 here. Then here SSY, which is 643.45 minus half into SSC dash, which is nothing but 314.16. So now entire equation, only Fs is unknown. So now if you simplify and if you evaluate this equation, you get the factor of safety as 1.26. So that is the solution for this particular problem. He asked us calculate what is the factor of safety only. So therefore the factor of safety is 1.26 only. So if you remember, while discussing about this fluctuating loads, we'll discuss about this factor of safety. So for springs, because we'll use very low factor of safety, which is always at max it is 1.5. The maximum value for the factor of safety is 1.5, or even sometimes it is less than 1.5. So the factor of safety here is we got it is 1.26 means. So as per our discussions, what we have discussed during the design of the springs against fluctuating loads about the factor of safety, this is within that range only. So this value is less than 1.5 only. So in most of the problems, if you solve any problem, you can counter check your solution. If you get factor of safety is more than 1.5 means you need to recheck your solution again whether you made any mistake in your solution or not, because so most of the spring problems, the factor of safety is it should be less than 1.5. So if you got an answer more than 1.5, let us say, okay, slightly more than 1.5, it is also okay. But if you get something like 5 or 6, factor of safety means your solution is wrong. You need to verify your solution and then you need to check the solution also. Okay, so this is how you can solve. So this problem is only purely finding out the factor of safety when a given spring is subjected to the fluctuating load, which is varying from minimum value to maximum value. Then, if I club the earlier we discussed how we can design the spring under static load. Now we calculated the factor of safety when a spring is subjected to a fluctuating load. Now we'll club these two things. So finally we can say that this is going to be the design procedure for the spring when it is subjected to, generally springs are subjected to fluctuating loads only. Even they are subjected to fluctuating load, how we are going to design the spring. So that we'll see in the next problem. So this is the problem what we are going to discuss, which will cover all the things whatever we discussed in the helical spring so far. That will cover, this problem will cover all those things, so that once you cover all these things, so I can assume that it is this topic is completed. Then we'll move on to the next topic. So that is leaf springs. Okay, anyway, before going into that leaf springs, first we'll discuss this problem and then we'll close this topic. So you note down this problem also, then we'll discuss. Take 1 or 2 minutes time to note it down. Once you completed that, just inform me so that we'll discuss the solution for this problem also. Okay, now you note it down. Okay, is it over?
Yes, sir.
Okay, right. So we'll see the now solution also. First, I'll go through the problem. What he has given. The construction details of an exhaust valve of a diesel engine are shown in the figure. The diameter of the valve is 32 mm and the suction pressure in the cylinder is 0.03 Newton per mm square. The mass of the valve is 50 grams. The weight of the valve lift is, that is, the maximum valve lift is 10 mm. The stiffness of the spring for the valve is 10 Newton per mm. The spring index can be assumed as 8. The permissible shear stress in the spring wire is recommended as 30% of the ultimate tensile strength. Neglect the effect of inertia forces. Design the spring for the static considerations and determine the factor of safety against the fluctuating loads. So that means he has given the two things. So first he asked you design the spring, but remember whenever you are designing the spring, you need to design the spring for only static loading. So that's why I said it is design the spring for static considerations, and then after designing it, then you can say that whether your spring is safe or not against the fluctuating loads just by determining the factor of safety. If the factor of safety is more than 1 and less than 1.5, you can say your spring design is safe or your spring design is okay, good. So like that we'll decide it. So that means first you need to design the spring for the static loading, then you need to determine what is the, or you need to check what is the factor of safety, whether the factor of safety is as per the requirement or not. So that is the thing. So that means the first problem is based on the static design of the spring under static loading. Then second part of the solution is you need to compute what is the factor of safety. So for that, first if I consider the static design, so while discussing all those problems, I already told to you, if you want to design the spring for static loading, you should know what is maximum value of P, what is the maximum load on the spring, and what is the deflection. So based on only these two parameters only, we can design the spring. So here he has given the delta value. So the maximum wall lift is 10 mm means the delta max is going to be 10 mm only. And instead of giving this P value, he has given the stiffness also. Stiffness of the spring K is also given. K is 10 Newton per mm. Of course, if you want, you can convert this one into meters also. In addition to that, how much load is acting on the spring? So that also you need to compute here. So that he has given indirectly. So what he has given is there. So this spring is used as an exhaust valve in the exhaust valve of a diesel engine. So now the valve diameter he has given 32 mm and there is a suction pressure on the valve. So that means, so the suction pressure will create a load on the spring. So you can see that here in this diagram here. So here you have a spring here. This is the valve here. So now a suction spring is there means, so here during suction stroke, this valve has to open. So valve has to open means, so it is something, some fluid, whatever may be the fuel for this one cylinder, it will go into the fuel mixture going into the cylinder. So therefore, this valve should be opened. So now during that suction stroke here, to open that valve, there is a pressure. That pressure is equal to 0.03 Newton per mm square he has given. So now if you know the diameter of the valve rod and this pressure, you can calculate what is the force on this valve rod. So that is nothing but ultimately it is going to act on the spring. So once you know these two things, then you can calculate the load, and in addition to that, what he has given is the valve has a mass also. It has a mass of, this valve has a mass of 50 grams. So that means the self weight of this valve will also act on the spring. So that is also another load you need to consider on the spring. One is the suction pressure, a load due to suction pressure, and this one. So what is that? Self weight of the valve. So those two will create a load on the spring. So based on that, we can compute the what is the load on the spring. Once you know the load, then he has given the other things, delta and these things are given. So and also he has given the C also. C is given as 8. So then only thing is first I can compute what is the wire diameter. Once I know the wire diameter, I can find the remaining parameters also as per the static design procedure. So that we already know that. So now I'll take you through those steps how we can do that. So first he has given the data. So that is stiffness of the spring is given as 10 Newton per mm, and C is 8 he has given, and tau is 0.3 times SUT. This is also he has given. Allowable shear stress is 30% of your SUT. That's what he mentioned here. If you look at the problem data, 30% of the ultimate strength is going to be your permissible shear stress. So that's what I written here. So now with this data, first you need to compute what is the wire diameter. For that, first you need to compute what is the spring force. What is the maximum force on the spring? The spring is subjected to fluctuating stresses. So therefore, oil hardened and tempered wall spring wire of grade VW is selected for this application. Why I written this statement here? Because in the problem data, he has not given the material properties. So your SUT is not given, even though he stated that the permissible shear stress is in the spring wire is recommended as 30% of the ultimate strength, but he has not mentioned what is the magnitude of this ultimate strength. That means he has not given the material properties for the spring. So then we need to pick those properties. So for that, what you have to do is, and also he has stated that you need to find the factor of safety against the fluctuating loads, means definitely the spring is subjected to fluctuating loads. So therefore, we need to select a material for the spring which can be withstand this fluctuating loads. So just now previous class we discussed about that there are two materials which when we use for the spring material against these fluctuating loads. Out of that, we'll choose this oil hardened and tempered wall spring of grade VW. So for that we know the material properties. So therefore, once you know all these things, then you can calculate what is the diameter of the wire. So and also here the load is changing from 50 newtons to initial load is initial there is a free load, and then the free load should be sufficient to wall the whole springs against the negative pressure inside the cylinder during the suction stroke. Since the cylinder is vertical and additional free load should be provided to account for the weight of the walls. So therefore, to calculate that load, first we need to compute what is the suction pressure, suction force, that is nothing but suction pressure multiplied by valve area. So he has given the wall diameter as 32 mm. So 5 by 4 into 32 square. D square is nothing but the area of the wall multiplied by the pressure. We get the, this is the force, 24.13 newtons is the force which is acting on the spring due to the suction pressure. And similarly, in addition to that, like I already mentioned, the self weight, that is self weight of the wall, which is nothing but mg. M is given as 0.5. What he has given? The weight of the wall, it is 5 grams or 50 grams. Yes, it is 50 grams. If I convert that one into kgs, it is going to be 0.05 kgs multiplied by gravitational force. So it comes out as 0.49. So therefore, if we add these two, that is going to be the total force acting on the spring. So therefore, minimum preload is this summation of these two. Minimum preload, that is the minimum load. Minimum load is suction force plus the weight of the wall. So that is comes out as 24.62 newtons. In addition to this, okay, so this is the preload. So since it is subjected to a fluctuating load, so he rounded off this 24 newtons to 30 newtons for safe side. So that means the minimum load is taken as 30 newtons. This minimum load comes from the suction pressure and the weight of the wall. Then you need to compute the maximum load also. So for that he has given the delta and K value. So during the exhaust stroke, the spring is further compressed by 10 mm. So therefore the maximum force acting on the spring is nothing but minimum load plus K into delta. So K is given and delta is given. So if you substitute those values, minimum load we are taking it as 30 and 10 into 10. K is 10, he has given Newton in mm only. So I'll substitute delta is also in mm. So from that I'll get the maximum load is 130 newtons. So now we need to design the spring for this maximum load. I am considering this load as a static load. So that means a maximum load of 130 newtons is acting on the spring. Taking this as a consideration, and we need to design the spring. So for that, first we will try to find out what is the diameter of the wall, right? So that is, again, you need to calculate what is the allowable shear stress, and then you need to find out what is the resultant shear stress. Based on the equating the allowable shear stress to the resultant shear stress, you will get the wire diameter. So for that, first you need to calculate what is the allowable shear stress, that is already given 0.3 SUT. So now for this, what is the material we are choosing? For the material what we are choosing for the spring, which is having a ultimate tensile strength of 1470. So if I substitute that, I'll get the allowable shear stress as 441 Newton per mm square. Then I'll calculate K value. So C is given as 8. If I substitute that 8 value into this formula for K, I got K as 1.184. Then use the formula for the resultant shear stress, which is nothing but K into 8 PC by pi d square. So substitute all the data. Allowable shear stress is 441, K is 1.184, P is 130 you need to consider here, and C is given as 8, not 80, 8. Then substitute pi d square. So only unknown is D. So if you solve this one, you will get D is equal to 2.67 mm, which may be rounded up to 3 mm. So that means we got the wire diameter as 3 mm. So once you have wire diameter, then you can find out the mean coil diameter also. The design is satisfactory and wire diameter should be 3 mm. However, spring is subjected to fluctuating stresses, and to account for these stresses, the wire diameter is increased to 4 mm. So here, why I written this statement is you may have a confusion. So from the calculations, we got only 2.67 and we rounded off that value to the 3 mm. But again, still why we are increasing that to 4 mm. So that is maybe the question. So if you have that doubt, then what you can do is you go along with the 3 mm only. You take the 3 mm and you do all the calculations and you check for the fatigue stress concentration factor. So once that fatigue stress concentration factor is stress concentration factor, it is factor of safety. If the factor of safety is within our desirable level, then it is okay. You can stick with the 3 mm, or else you need to increase the diameter of the wire. So that I already done it here before going to the calculation itself. So by assuming some factor of safety here, I have taken that one as 4. So with this 4, I will proceed with the further calculations. Or else, if you want, you can take 3 mm and you do all the things, and then you calculate what is the factor of safety. Still, if you feel that the factor of safety is sufficient for these calculations, then you can go along with this 3 mm diameter only. Okay, so that is the point you need to remember here. So now, once I got the small d, then capital D is going to be C into D, which is 32 mm. Number of active coils is, again, the formula for that is GD power by 8 into D cube into K. So G is 81370. Of course, this data is not given in this particular problem, but we need to pick these values from the data book. If it is not given in the problem data, you have to use the data book to pick the values. So D comes out as 4 and capital D given as 32 and K, stiffness of the spring, is 10. So from this formula, you will get your active number of coils is 7.95, which should be rounded up to 8 coils. Then you need to calculate what are the total number of coils just by assuming some type of ends for the spring. So generally we will use square and ground ends, which has 2 inactive number of coils. Therefore, your total number of coils will become 8 plus 2, which is going to be 10. Once you have this, then you need to compute what is the free length of the spring. So to compute the free length of the spring, you require what is solid length, what is the axial deflection, and also what is the total gap between the adjacent coils. So for that, first we'll compute what is the axial deflection. The formula is this one, 8 PD cube n by GD power 4. If you substitute that, the axial deflection is 13.09, but here he has given only 10 mm. So therefore, you have to take this one as the axial deflection for the given diameters. Then solid length is now total number of coils multiplied by wire diameter comes out as 40 mm, and the gap of 0.5 mm is assumed between the consecutive coils. So therefore, the total gap is going to be 10 minus 1 into 0.5 comes out as 4.5 mm. So now I know all the 3 parameters, that is solid length, total gap and delta. I'll substitute those 3, 40 plus 4.5 plus 13.09. So you'll get it as 57.59, which comes out as, or which may be rounded up to 60 mm. So once you have a free length, then you can find the pitch of the coil. Pitch of the coil is nothing but free length by total number of coils minus 1, which is 9. So 60 divided by 9 gives you 6.67 mm. So this is about the design of the spring by considering the load as a static one. So once you are done this, then you need to check for what is the factor of safety. So this is the procedure what we discussed in the previous, not in the previous problem. Before that, we discussed some 3 or 4 problems. In those 4 problems, we discussed the same procedure. But only thing what we done here it is not going to be different. Only thing is how we are calculating the load is different here. So he has given us some wall application and he has given the suction pressure and weight of the wall. Based on that, we computed what is the load acting or total load acting on the spring. Then once you've done that, then you need to go for calculation of the safety factor. So for that, you need to compute what is amplitude stress and what is the mean stress. So that once you have designed the spring, means you have all parameters with you, then use those parameters to find out what is tau m and what is tau a. So tau m is nothing but Ks into, this is the formula what we already discussed. If you substitute all those parameters, it comes out as 108.23. Similarly, tau a comes out as 75.38 Newton per mm square. So then once you have tau m and tau a and also choosing the material, so then you need to, for that material, our SSC dash is 323.4 Newton per mm square and SSY is 735 Newton per mm square. So now use these 4 parameters and substitute into this equation so that you can compute your factor of safety. So here, if I substitute all this data and if I evaluate it, the factor of safety comes out as 1.85. So it may be more than 1.5. So why? Because I've taken the diameter on higher side. So I got from the calculation, I got D is equal to 3 mm, but I made it to 4 mm. With 4 mm, I got a factor of safety of 1.85. So if you want, you go proceed with the 3 mm also, you check what is the factor of safety you are getting. If the factor of safety is more than 1.2, then it's okay, but design is safe. Okay, so this is how you can solve that when two things are clubbed into single problem. So in this problem, what he has given is, he asks you to design the spring for the static loading, and after the design the spring and ask you find out what is the factor of safety for the fluctuating load also. So for that, entire data is given except the material properties. So material properties is not given in the problem. Maybe sometimes they may give those properties also. If not, they are not given, then what you have to do is you have to use your data book to pick these values. So, or else if you don't know how to choose the values from the data book, then you cannot solve the problem. So you need to write clearly in the problem data and choosing this and this is the going to be the material for the spring. So for the spring material, if the material is this one, then these are the properties. You need to write them clearly, then only you need to proceed for the solution. Okay, I think this is about this helical springs, whether they are under compression or tension. So next thing is, next class, maybe already 10 more minutes is there. Okay, anyway, we'll discuss the leaf springs in the coming classes. So now, before closing this, I want to make sure that if you have any doubts for you, you have to clarify. You need to clarify your doubts. Then only we'll move on to the next topic. So you need to note down all these calculations and you need to upload this one in the classroom. So in also, if you have any doubt in this problem or maybe in the previous problems or maybe any topic on this helical compression spring, any problem in the helical compression spring, you can ask our doubts also. So that we'll discuss our doubts and then we can close this topic. So for today, we are not going to discuss that leaf springs. Maybe next class we'll start that. So if you have any doubts, you can ask our doubts so that you can clarify our doubts and also we can close this topic. Maybe for this class, you need to, if you are already noted down this one, then what you need to do is, so like I already told here, so after calculating the wire diameter, we got it as 3 mm here. So then instead of 3 mm, we made that one as a 4 mm by assuming some factor of safety here and we calculated or we did the springs. So for this 4 mm, we got 1.85 as the factor of safety. So now instead of 4 mm, just you proceed with 3 mm diameter and do the calculations and find the what is the factor of safety. So once you identify the factor of safety, then you tell me what is the answer, whether the design is acceptable or not. Or you can say that by this here the assumption, that is making the wire diameter instead of 3 mm, if I choose the 4 mm, is it a valid one or not? That also you can state that. So even with 3 mm diameter also you are getting a factor of safety of 1.5, means there is no sense or no need of making the wire diameter is 4 mm. So you can go for only 3 mm. But only thing here is, see, if you go for the 3 mm here, okay, anyway, so that is fixed. Only spring index is fixed as 8, means no issue. So you can calculate the parameters and you can check whether you are getting the required factor of safety or not. Okay, so if you have any doubt, then you can ask it. So, or else I'll stop the class today at this point. You just try to compute all these things and then upload in the classroom. So in the next class, we'll see the leaf spring. From next class onwards, we'll see the leaf springs.